What's up, everybody? Hope you're all doing well today. We're going to be looking at some rotational motion problems, and we're really just going to be looking at what I consider part one of this section. So the focus will be on torque. So we'll do some equilibrium problems where all torques are balanced, and then we'll also be doing some non-balanced situations where essentially you're going to be summing up your torques and finding the angular acceleration. As usual, you should be trying these out first on your own and then checking your answers with my videos. All right, let's go ahead and get started. So our first question, we're going to be examining kind of your classic seesaw problem. So we have one child on the left here. They have a mass of 35 kilograms. We have another child on the right. They have a mass of 20 kilograms. And then we have the actual board itself. Sometimes they'll say the beam is massless, or they'll say the word light, but here they definitely are not. And so as long as it's a uniform beam, as this one is, we're going to say that the center of mass of that beam is right there in the literal center, meaning from here to here, the whole thing would be 1.5, right? From the pivot point, this would be 0.5 meters. And this has a mass of 15 kilograms. All right, so here's our axis of rotation, and we're basically just going to set up a torque equality. So we'll say all the counterclockwise torques should balance out with all the clockwise torques. So on the left, we have a counterclockwise torque. That guy is 35 kilograms, and technically it's times little g to give us a full weight, a full force. So I'll just write g for now. That distance they give us to be 0.6. And then the clockwise torques, you have the kid on the right. That kid's 20 kilograms times little g. And the distance is unknown. We're looking for that distance. Plus, the board itself has a torque. That's going to be 15 kilograms, also times little g. And that distance is 0.5 meters. So we're just solving for g here, for d, distance. Notice that all the little g's do cancel out. And there we go. So let's go ahead and do this algebra. So 35 times 0.6, that's giving us 21 equals 20d plus 15 times 0.5, that's 7.5. Subtract 7.5 from both sides. We have 21 minus 7.5 gives us 13.5, and then we'll go ahead and divide by 20. So 13.5 divided by 20 equals d, and we get 0.675 meters. So that would be the distance that this little kid needs to sit from the axis of rotation, from the pivot point, to balance this out. All right, let's move on to the next one. All right, so in this one, we have our painter standing on a board. The painter is 75 kilograms. Distance is already marked. Now, does the board have a mass? Yep, sure does. So we're going to include the board's mass. We're going to find the center of that mass. Since it's a 5-meter board, that means the center should be 2.5 from each side. And the mass of that was 16 kilograms. All right, so to solve this one, we're going to first go ahead and do like a free body diagram here. So our free body diagram, we're going to always do it at where things are located. So we have the FG of the board, the weight of the board. We have the FG of the painter. Okay, I guess they're technically way bigger, but I'm not going to draw that to scale. So the FG of the painter is going to be 75, well, 75 times g. And then we have these two ladders kind of exerting an upward normal force here. So let's call this the F of the left ladder, and then the same thing on this side. This one, hopefully you can see this one should be slightly bigger because the painter is offset on that side. So we'll go F of the right ladder. So the next step after you've done your free body is to do our summations. So we're going to do two summations here. we're going to do our usual force summation. And this should be fairly easy to notice, right? The two weights are going to have to balance out with the two ladder forces. So I'm going to go F ladder plus, F left plus F right. And that should balance out with the two weights. So we have Fg of the board plus Fg of the painter. So those two should be in equilibrium. And then the next thing we're going to do is we're going to sum up our torques. So when we sum up our torques, we have to first find an axis of rotation. So it doesn't really matter, you could use literally anything. I typically like to use either the far left or the far right. So I will just use the far left in this case. So we just look at all the torques. Now we notice these two torques from the weight are going to produce counterclockwise torques. And then the force of this right ladder is going to produce a counterclockwise torque. And then the ladder on the left, since we're at the axis of rotation, will produce no torque. So let's go ahead and set up this. So I'll go force of the right ladder times the distance away. Okay, that distance was 5 meters. That should balance out, so we'll make that one positive since it's counterclockwise, and then the two clockwise torques will subtract. So we'll go Fg from the board times the distance of 2.5 meters, and then we'll go also minus Fg from the painter, and that one is 3.5 meters away. Okay, that should equal 0 since we're in equilibrium here. Another way of looking at it is we could have just set the torques equal, right? So force right times 5 should equal, let's go ahead and plug in these numbers here. So the force G from the board, that was what, 16? And notice this time our little g's aren't going to cancel, so we're going to just leave it in there as 9.8 times 2.5, and then plus the painter's force. They were 75, their weight, right? 75 times 9.8, and they are 3.5 meters away. Okay, so let's go ahead and do the algebra here. So just multiply, multiply that, add that together, and then divide by 5. I'll let you take care of the algebra, and I will go ahead and calculate it now. And I get 593 newtons. So make sure you're able to get what I got. So then what we're going to do, we're going to go back up to this original force summation that we have up here. So this one we had force left, right? Plus, and then we'll just plug in what we got on the force right. So that was 593 newtons. And then the force G on the board, again, this would be 16 times 9.8 plus force G from the painter, the weight of the painter, that's going to be 75 times 9.8. And there you go. Let's just go ahead and solve for that. So I get 299 newtons for the left side force. So you do want to make sure that your answers make sense. For example, the force on the right, as we said, the force on the right should be larger, the ladder on the right, because the painter's offset over in that direction, right? So, yep, sounds good. All right, let's go ahead and move on to the next one. All right, so this is one of these angled tension problems. And let's just go ahead and set this one up. So we have our board. Again, it has a mass, so we're going to include the mass here. We'll include that mass right at the midpoint here, right? So this was 75 kilograms. And since we're right at the midpoint, this should be 3 meters away from both sides. 75 kilograms. Okay, we have our load. Our load is unknown. Oh, we're actually solving for the load here. So this is our unknown here. And this time they do give us the tension. A lot of times they ask for the tension, but this time they give it to us. So our tension here is 2,400 newtons. That's the max tension. The question's essentially saying, like, as you add more mass, as the mass increases, the tension will increase. So we're looking for like the maximum mass to give us this 2400 newtons of tension. Okay, all right, so as usual, we should be doing our free body diagram, and we'll do it at the point of contact. So we have the mass of the load here, or let's just call it mg. And then this one we have 75 kilograms. We'll draw it way down here. So this would be the mg of this one, I guess. Let's just solve it. So 75 times 9.8. If you don't mind, I'm just going to use a nice 10 for this just to keep it simple. So that should be about 750 newtons. Now the tension in this rope is given as 2400. Now what we do want to do is notice that part of our tension is going to be pulling up here. Let's call that Ty. And then part of the tension is going to go horizontal. Let's call that Tx. So if you look at our triangle, let me do this kind of off on the side here. So this is 2400. This is 37. So there's this Tx, which would be 2400 cosine 37. And then we have our Ty, which would be 2400 sine of 37. So let's just go ahead and do the math on that. 2400 sine of 37 gets me 1444. And then 2400 cosine of 37 gets me 1917. All right, so the next thing we're going to do is we're going to do our summations. So this time we actually have 3 summations to worry about. So we're going to do our force summation in the x direction. So one thing I should say that I just kind of overlooked, but there's actually like a little hinge right here that has to hold this into place, right? And so that hinge is going to also kind of be pulling up. It's going to have a vertical component. Let's call that H hinge Y. And then it's going to also push this direction. Let's call it hinge X. Right? So you imagine if there was not this hinge here, the whole board would just collapse downwards, right? So we kind of need that there. So anyways, that's going to do us to our x summation. So our x summation, we have, well, that hinge going to the right, and that's going to have to balance out with the tension in the x direction. Okay, now we already found that, so let's just go ahead and continue this. So the tension in the x direction we found to be 1917 newtons. So we know the horizontal hinge is going to be 1917. And that just has to balance out with the tension, like the rope's pulling us this way, right? Part of it is pulling it this way, and so the board has to push back, or the wall has to push back. All right, let's do the y side, vertical forces. So this one we have Ty going up. We have the hinge Y also going up. And then we have the 2 weights coming down, right? So that should equal the board's weight, which we already found to be 750, and then the mg coming down, the mg from the unknown mass, right, coming down. So this one we have 2 unknowns, so I think I'm going to leave it as is for now. Let me get us a little bit more space here. All right, then the last thing is we're going to do all our torque summations, right? Why don't we do a different color this time? So we do our torque summations. We do have to define an axis of rotation. Now I think since we don't know the hinge, that would be the logical axis of rotation to use. So we have this, let's just label them on this. So we have the tension, kind of this rope that's pulling up counterclockwise. Then we have the weight of the board that's pulling down clockwise. We also have the mass unknown clockwise as well. So when we sum up our torques, we're going to have Ty, and we actually know that, but I'll just leave it as a variable for now. Ty times 2 meters, okay, plus, no, minus, right, because it's in the opposite direction. Actually, why don't we just do this? Why don't we just say equals, because we know that counterclockwise torques should equal the clockwise torques. So we're going to go the weight of the board, which is 750, times that distance, 3 meters. It's getting a little bit messy in there. 3 meters. And then we have the weight of the board, which we don't know, so we'll go M. I've been using 10 for little g, so let's go ahead and do that. And then the distance is 3.5 meters away. Okay, so remember, we do know Ty. We found that earlier. Ty is right here, 1444. 1444 times 2 equals 750 times, that's what, 2250? Plus 10 times 3.5 is 35, so that's 35 M. All right, let's go ahead and do this out. Remember, we're solving for M. So I got 1444 times 2, subtract 2250, and then divide by 35. So I'm getting 18.2 for the mass. All right. I see the answer says 20. I'm pretty sure that's rounding to one digit. Maybe, and also I use 9.8, right? So it might be slightly off based on that. So I'm going to be confident in that answer. All right, the next one, what is the force from the hinge? So we've already found one hinge force, right? That was Hx. Now we're just solving for the other hinge force, Hy. So at this point, we now know Ty, or we knew it, 1444 plus hinge y equals 750 times the mass, which is 18.2 times little g. So let's just go with 182 newtons. Okay, so let's solve for Hy. So we're going to go 750 plus 182, and then we'll subtract 1444. And interesting enough, for Hy, I'm getting a negative number. So what does that mean? Well, I assumed that Hy was going to go up, but as you can see, Hy is actually negative, so it's actually coming down like this. So we have our Hy 512 coming down, and then earlier we found Hx to be 1917 newtons. So looking for the total force from the hinge, we'll just use the Pythagorean theorem to get that. So we'll go ahead and go 512 squared plus 1917 squared, and then we'll square root that, and I get about 1984 for the hinge force. And then we will find the angle based on this triangle that I'm drawing. We'll find this angle right here. So we'll go inverse tangent of 1917 divided by 512. And that looks 75 degrees. We'll put with the vertical. Okay, or we could do our little northeast-south direction based on this angle that I drew right here. That would be east of south. Okay, all right, that was a long one, but good. Let's move on to the next one. So this should be a much easier problem than the one we just did. Notice we have kind of a wheel. We have kind of two radiuses of this wheel. We're looking for the net torque, so let's do that first. So torque net, that's just like the sum of our clockwise and counterclockwise torques. So let's do the counterclockwise torques first. So 12 newtons is going to apply a counterclockwise torque at the A radius, which is 0.1 centimeters or 0.1 meters. The 10 newtons is going to produce a clockwise torque. Likewise, the 9 newtons clockwise torque. So we'll subtract for those. So we'll go minus 10. And this is at the distance of B, right? So B is 0.25 meters. And then the 9 is also at 0.25 meters. Okay, so we got 12 times 0.1, that's 1.2, minus, what's that, 2.5, minus 9 times 0.25 is, what's that, a quarter, 4, 9/4, 2.25. Okay, and that gets us a negative 3.55 Newton meters. So what's a negative mean? Well, that just means that it's moving in the clockwise direction. Okay, and again, we defined counterclockwise as positive and clockwise as negative. And you can actually see clearly that these two torques are much greater than the counterclockwise torque. All right, let's find the angular acceleration. So that's pretty easy, right? So we'll go net torque equals I times alpha. Now we do need to find the inertia here. So they're saying assuming it's a solid disk. So remember, the inertia for a solid disk is 1/2 mass times the radius squared. So the mass they gave us was 0.6 kilograms. The radius, well, this is going to be the large radius, right? That's what the radius is, the big radius here. So that'd be 0.25 squared. So when we do this, we get 0.5 times 0.6 times 0.25 squared. I get 0.01875. Again, the units would be kilogram meters squared. So we got negative 3.55 equals 0.01875 times alpha. So the alpha is going to be 189 radians per second squared. Technically that's negative, but again, all that means is that it's moving in the clockwise direction. All right, let's move on to the next one. All right, so this is one of these Atwood machine type problems. We have a mass here that's going to be coming down, and then the string is going to be kind of wrapped around this pulley here, right? And we're going to include the mass of the pulley. Obviously, if we didn't, then it would just fall with a little g, right? 9.8. So we are going to figure out what the acceleration is, including the mass of the pulley. So as usual, we'll do our free body diagram. So we have the kind of the mg here of the mass falling down. We have the tension pulling back up in this direction. And then over here on the pulley itself, there's going to be a tension coming down. Okay, so let's do our summation. So we have two summations because we have two masses here. So the first one is a force summation on the mass falling. So we're going to go mg minus tension should equal ma. And remember, we do want the direction of rotation to be kind of our positive direction. So the pulley is rotating clockwise and this mass is falling. So we're going to call that the positive direction for both. So this one's technically has an angular acceleration, right? Because it's rotating. So the next thing we're going to do is we're going to sum up our torque on the pulley. Okay, so the torque on the pulley is going to be the tension times the radius of the pulley. And that's it. That's the only torque, right? Here's our torque exerted right at that location. And that should be equal to I times alpha. So that's our two equations. There are multiple unknowns here. Ultimately, we're solving for the acceleration first. So we'll go ahead and solve for that first. So remember alpha. Let's relate alpha and a. So remember, a is equal to alpha times radius. So at this point, let me change my color here. At this point here, the rope is accelerating this way, right, with a. And at the same time, it has an angular acceleration at that point, alpha. And the relationship between those two is that a is equal to alpha times r. Or another way you could say that is alpha is equal to a divided by r. So right here, let's go ahead and do I. So remember, this is a solid pulley, is that right? Let me double check. Solid cylinder, yeah. So we're going to go 1/2 the mass of the pulley times its radius squared times, and we'll substitute in this alpha here, A divided by R. So notice one R cancels, and then over on this side, remember we had torque times the radius, that R also cancels. So what we're left with is torque equals 1/2 mass, this is the mass of the pulley, times A. To continue the problem, we're going to go ahead and solve this tension, not solve, but substitute that tension up there. Let me make a little bit of more space for us. So let's rewrite this. I'll go back to blue here. So we're going to rewrite this right here. So we got mg, remember that's the falling m, minus, now we're making the substitution for tension, and then that equals big M times A. All right, let's solve for the acceleration. So we got big mg equals big MA plus 1/2 mass of pulley times A. Again, let's solve for A. So A would be equal to, A times M plus 1/2 M pulley. And then let's just leave it in variable form just for fun, or just to practice doing that. So we're going to have mg, we're going to divide by M plus 1/2 mass of pulley equals A. Okay, solve for A, so plug in all the numbers. I'm going to go ahead and do that, and you see if you can get what I get. And I get 3.92 meters per second squared. All right, what's the angular acceleration of the cylinder? So we kind of already set this one up for us, right? That would be right here, right? Alpha is equal to A over R. So alpha is equal to 3.92 divided by the radius of the pulley, which was 0.04 centimeters. So 392 divided by 0.04 gets me 98 radians per second squared. All right, and the next is a conceptual question. So what if the pulley was negligible? How would that affect your acceleration? I guess we already stated this. If the pulley's mass was negligible, right, if m was essentially 0, well here, let's just see what would happen. If the mass was 0, this goes to 0, right? And then you just have mg over m, which means that mass would cancel, so A would be equal to g, which should make sense, right? If we're not considering the mass of the pulley, it's as if this mass was just falling, and it would fall with little g. All right, let's move on to the next one. So here we have our classic merry-go-round problem. So here's our merry-go-round. We're going to say it's a solid disc. 1.5 meter radius, so that's from here to here is 1.5. Okay, and the mass is 150. And we're going to put a kind of a rope on here, I guess. And we're going to pull on the rope. And that's going to cause it to move. Okay, so let's see. What force must be exerted to move the merry-go-round from rest to an angular speed of this? All right. So we're going to ultimately, we're looking for force, right? Let's just go through how we're going to be approaching this. So we're looking for force. So we're going to be summing up our torques. That equals I alpha. The I we can find easy enough, right? It's a solid disk. The torque would be the force times the radius. They do give us a radius, so we have to find the force, right? That's what we're looking for. But to find the force, we have to find the angular acceleration, and then it's a straightforward problem. So to find the angular acceleration, they do give us a few things. They give us 0.5 revolutions per second. That's kind of our final omega here that we're looking for, right? So we do want to change this to radians per second. Remember, 0.5 revolutions 1 revolution is 2 pi radians, right? So essentially that's equal to pi radians per second. That should be kind of obvious, right? If it's going a half a revolution in a second, then it's going pi radians in a second. Okay, so we're going to use some angular kinematics. So omega final we just found. Omega initial, it says it's from rest. And it tells us the time as well as 2 seconds. So again, we want to be trying to find the angular acceleration so that we can find the force. So we'll use this equation, omega final equals omega initial plus alpha times t. So we have pi radians per second equals 0 plus alpha times 2 seconds. So alpha we could see is pi over 2 radians per second squared. All right, and then we'll go ahead and throw that into our little summation that we set up. Okay, let's go ahead and do that down here. So we got force times the radius. Our radius was 1.5 equals I alpha. Let's find our I. So remember, they said it was a solid disk. So that's going to be 1/2 m of the merry-go-round times the radius squared. So that's 1/2. The m was 150, and the radius was 1.5. And we'll square that. Okay, so I'm getting inertia of 0.5 times 150 times 1.5 squared, 168.75 kilogram meters squared. So 168.75, and then we'll use the alpha that we got, which is pi over 2. Okay, so that times pi, 168.75 times pi divided by 2, and then we'll also divide by 1.5, and I'm getting 177 newtons. Okay, so that should be the force. All right, what force is needed if there's a 50 kilogram person? So now we're going to stick a person. Are they on the edge? They are on the edge. So we're going to stick a person right here. Okay, so as you might imagine, putting a person there means it's going to be harder to move it around, right? So if it's harder to move around, that's because the inertia is going to change. So there's going to be an inertia of the person here, and we're going to just add that to the inertia of the merry-go-round. So we're going to treat a single person as a point mass moving around. So that would have a inertia of mr squared. So the inertia of the person is going to be, how big were they? 50. And then they're at a distance of 1.5 squared. So 50 times 1.5 squared means their inertia is 112.5 kilogram meters squared. So that means I total, we're just going to add up those two, the 168 and the 112. And when I add those two, I get about 281. Okay, to be more precise, 281.25 kilogram meters squared. All right, so to find a force, that should be straightforward. We're just going to throw in this new value into there, right? So we'd go force times 1.5 equals, we'll do our new inertia, 281.25 times pi over 2. Okay, solve for force. So 281.25 times pi divided by 2, and then we'll divide by 1.5. And I'm getting about 295 newtons. So as you might imagine, it's greater, right? It's greater than the 177 we got. Notice it's almost double, and that's because, well, adding that person didn't quite double, but it almost doubled the total inertia. All right, let's go ahead and move on to, is this our last one? Yeah, this is our last one. All right, so our final problem is a gorgeous problem. We are looking at this like it's a bike. So let's just set it up and then we'll go ahead and solve it. So you have your bike chain right here, right? It's going to be kind of wrapped around and it's going to be applying a force, or more specifically a torque, on our bike sprocket there. Okay, so that's going to cause like a clockwise motion here. But then you have the resistance with the ground, right? So as this is with the ground, there's going to be kind of this frictional resistance opposing, producing kind of a counterclockwise torque. And so we're looking for kind of this net acceleration, right? Angular acceleration. So we'll sum up our torques, and essentially what we have is we have kind of this force from the chain. All right, force chain. Well, the torque from the chain. Okay, so this is going to be times R2, and then we're going to subtract out this resistance force. So force R times its radius, and this is a larger radius, right? So this we're calling R1. So that's our two torques. That'll give us our net torque, and then that's equal to I times alpha. All right, that's it. That's all we have to do to solve it. So we are looking for the force from the chain, right? That's what we're looking for here. So let's go ahead and plug in some numbers. So force of the chain, we don't know. The radius 2, that's the small radius, right? So that's going to be 4.5 centimeters, so 0.045 meters, minus the resistive force. So that one, they actually give us a number, right? That's how much, 120. And then we'll use the big radius there, that's R1. R1 is a distance of 0.32 meters. And then this is the inertia of the bike wheel. So they're assuming that it's like a hoop, like a hollow hoop here. All the mass is concentrated on the outside radius. So remember, for a hollow hoop, let's just do this on the side. This is just mr squared. So even though, you know, this chain, obviously the sprocket has some inertia, but most of it, to be honest, is going to be the outside, right? That big radius is going to dominate everything. And they're saying just go ahead and assume that that's all of the inertia. So the mass of the bike wheel was 1.8, and then the radius, again, was 0.32. So we got the I of the hoop is going to be 1.8 times 0.32. Oops, don't forget to square that. So 1.8 times 0.32 squared gets me 0.184 kilogram meters squared. So let's go ahead and fill that in. 0.84 times alpha. Actually, we know alpha, don't we? Alpha was 4 radians per second. All right, so let's do the math on this. I'll do a little bit of algebra today. 0.184 times 4 gives me 0.736. 120 times 0.32 gives me 38.4. Okay, and that is what, FC times 0.045. Okay, so we'll go ahead and add 38.4 to both sides. 0.736. So it's giving me 39.136 equals FC times 0.045. Divide both sides by 0.045, and I get about 870. 870. Okay, so that's how much force you have to exert by the chain. I mean, ultimately it's by your legs, right? So your legs are rotating it, and the pedals, actually that's even a better problem because they have to rotate the pedals. Those have a torque themselves depending on, you know, the diameter of the pedals. Not the pedals, but like the circle the pedals go around. And then that's going to ultimately move the chain. But we're not doing that. We're not making it that hard. We're just going to move on to letter B. If the force is applied for 5 seconds, how many rotations will it make? Okay, so ultimately what we're looking for here is like what we call theta, right? That's going to give us the number of radians that it goes through in this time. And then we can solve for revolutions once we know the radians. So let's write down what we know. So we know omega initial is 0. We know alpha was something 4. And they give us a time, right? 5 seconds. So from there, we'll choose our equation that's going to work for us here. I think it's going to be this one. So we're going to go theta equals omega initial times time plus 1/2 alpha t squared. Omega initial is 0, so this is going to be 1/2. Alpha is 4. T is 5 seconds, so 5 squared. So that gives us, what's that give us? 50. 50 radians. All right, remember 1 revolution is 2 pi radians. So we're going to go 50 radians divided by 2 pi. And that gives us, what does that give us? 25 divided by pi gives me about 8. Okay, if we want to be precise, 7.96 revolutions. All right, so that's it for these review problems. Again, remember, this is just the first half of the unit. We'll do the second half a little bit later, where we'll look at angular momentum and rotational energy, that kind of thing. But for now, we'll stop here. So let me know if you have any questions, and I will talk to you soon.